Hey everyone, I hope everyone's having a good day. This is T.A. Yusuf, and today I'm going to be doing a video on Laplace transform in circuits. So hopefully in this video, I'll walk you through how we can get to the Laplace transforms when initial conditions are zero for our three main components. I can explain the advantages of having Laplace transforms and using those in circuits, and then we can also work out a problem fully. So let's dive right in. So one of the main advantages of using Laplace transforms in circuits is that it can simplify our differential equations. It can simplify those large functions that we're working with, whether that's our sine waves or whether if it's our exponents using e to the x, or e to the tau. It can simplify a lot of those. Laplace can not only simplify that, it can also simplify any signals we have with logs, with natural logs, or any other little bit more difficult functions. And it'll simplify it into operations such as multiplication, addition, subtraction, and addition, where we're all a little bit more comfortable working with. Another benefit of working with Laplace transforms is it's going to help us with our gain calculations. And gain is our ratio. In this problem, we're going to be talking about our V out over our V in, so our voltage gain. But it really can be our output, a ratio of our output over our input for multiple things. It can be your sound gain, it could be your frequency gain, it could be a lot of different things. In this problem, we're going to be talking about our voltage gain. So our output over our input, and we're going to be talking about that ratio. And Laplace helps us find our ratio without without needing an actual signal or a value to our V1. And then something else that Laplace transforms can help us with is our frequency analysis. With our components that are reactive, such as our capacitors and our inductors, Laplace can help explain a little bit more in detail about how they will behave with frequency. When we change our frequency, what's going to happen to our circuit? What's going to happen to our inductor? What's going to happen to our capacitor? So those are just three benefits of doing Laplace transforms. So before we get to our circuit, I'm going to go over this table we have on the left side, and then I'm going to explain how we get to that part of the table. So this first part of our table, we're talking about R and R. So on the left side, we just have our components. We have our resistor, our capacitor, and our inductor. And then we're taking the Laplace transform of that component, and that Laplace transform is what we're going to use in our circuit to start solving for the answers we want to find. What we find is for our resistor that the value of R is going to be the same in the time domain, which is if we're thinking V of t, and it's also going to be the same in the S domain, or the frequency domain, V of s. So our Laplace transform of R is just going to be R, and this should make sense if we remember in differential equations when we did Laplace transforms. Whenever we're doing a Laplace transform of a constant, the constant just comes out. And then the next one on our list, I'm going to switch colors here. We're working with our capacitor. And our table is saying for our capacitor, the generic Laplace transformation when the initial conditions are zero is going to be 1 over S multiplied by C. So in the denominator, we have our S and we have our C. So this is telling us that in the time domain is different from the S domain for our capacitor. And so I'm going to go to the right side of the screen, and we're going to try to find why that is. So I'm starting here up top. This is what we're given, and we're going to try to figure out why. Why are we using this equation as opposed to something else? Where did this come from? So if we're starting at the very basics and we're talking about our capacitors and a frequency of time. So if you see here, I have my current as a function of time, and I have this equation on the right. You might be also asking, where does this equation come from? This equation comes from what we know about our capacitor. Remember that a capacitor, the current going through the capacitor is based on the change in voltage over time times that capacitance. So this is one of those early equations that we use just to describe a capacitor. And this should make sense because we're thinking about, okay, this voltage is going to start collecting on both sides, and that's going to happen over time, which is representative by our derivative here. And then we can finally, once this is charged, our current can start going through. So that's where this equation comes from. It comes from those basics of capacitors that we learned. So I'm going to take this equation and I'm going to do the Laplace transform of both sides, and that's going to help me reach an answer of how I got to the equation in my table. So if I take the Laplace transform of both sides, okay, remember, so now this left side is just going to become I of S. So the current is now based on a function of S instead of T. That was my Laplace transform for that side. And then for my right side, I have my C, my capacitance. Laplace transform of the capacitance, we can just take it out, it's a constant. And then this next part is the tricky part where we have to remember. I'm going to do it in a separate color. This next part is a tricky part we have to remember. If I go to the left side of my board, I wrote an important note for myself. When we're taking the Laplace transform of a derivative, what we'll always get is S multiplied by that function and then minus the initial condition. So this is plugging in 0 for our function or our initial condition, and we're going to have S multiplied by the function. And that's going to be our Laplace transform of our, so we're going to be using that equation. So I'm going to have S times the function as a frequency of S, so S times V sub S, and then minus that initial condition. Initial condition is going to be V, and then I can say 0 minus. This minus is saying we're at time 0 before anything happens. So the next step, a part of this, I'm going to distribute over my constant, the C. I'm going to have S times V sub S times C, and then minus my initial condition times C. And here we're really working with when our initial conditions are 0, because we're thinking at the beginning of our capacitor, there's no voltage across our capacitor. Our capacitor is not charged yet. So if I'm thinking about my initial condition is 0, 0 times capacitance, doesn't matter what my number is, I can cross out this right side of my section. So now I have I of S is equal to S times Vs of C. Okay, and now we're almost done here. And if we want to talk about how we can describe the behavior of the capacitor, a lot of times we always go back to Ohm's law or our variation of Ohm's law. And if we're comparing these two equations, I have two of those same components already here, except they're just being talked about in the S domain. So I have my V of S and I have my I of S. So now I'm going to do some algebra and I'm going to manipulate my equation to reflect something I can talk about, the ratio of voltage over current. So I'm looking for V over I. Okay? So V of S over I of S. If I'm thinking I'm moving this to the other side and then my S and C to the other side, the equation I'll get is 1 over S times C when those initial conditions are 0. So that's how I got to that first step for my capacitor. So now we're going to go back and do that same thing, but for the inductor. I might be running out of space here, so I'm going to rewrite it on the other side, and we can change colors again. So this same idea, we're saying L equals S times L, This is what is given in our table. And once again, why? Why is it shown to us? How did we get here? So if we go back to our basics of an inductor, as a function of time, that is based on the rate of change of the current going through the inductor. And we're going to do that same process. We're going to use our equation here for taking the Laplace of a derivative, and we're going to take the Laplace of both sides of our equation. So let's go ahead and do that. Laplace of v of t and the Laplace of L di dt. Okay? So I'm going to scroll down. Remember, when I take the Laplace of this, I'm just talking about my voltage now in the S domain. When I'm taking the Laplace of my L, the L can be on the outside of my equation because it is a constant. And now I'm going to have S times I of S. So that's my function. And then it's going to be minus my initial condition. In this case, the initial condition is going to be the current this time. Same idea as before. We can distribute out the L to both. And we're going to have S times I of S times L minus the initial condition multiplied by L. And if I'm thinking about my basic inductor at the beginning, initial condition, there is no current flowing. My inductor wants to oppose the change in current, and it's acting as an open circuit. So if it's an open circuit, my current for my initial condition, I'm assuming to be 0. I can cross out the right side of this equation. And once again, I have V of S is equal to S times I of S times L. And now when I move over a couple of things, I'm going to have V of S over I of S, S times L, and that's the equation I see in my table. So, quick recap of what we just did. We talked about the capacitor, we talked about the resistor and the inductor, and how they compare in the frequency domain and how they compared in the time domain. We showed how we got those equations shown in our table above, and we explained how we got there using those Laplace transforms. Now that we have done that, we can go start tackling our problem. And in this problem, we're assuming those initial conditions are 0, so I'm going to choose directly from my table. So let's zoom in on this problem here. In this problem, they want us to know, they just want us to find the gain of this circuit. They have labeled a couple things for us, which will help. They have labeled V out. They have labeled V in. We aren't given the value of V in, but this won't be an issue to us. And some other things that we know all the values of the components. So I'm going to just go ahead and label that. 10 ohms is the R1, 2 ohms is R2, and 3H or 3 henries is our L1. And based off of our table, if I was doing the generic Laplace transform for my inductor, I'm going to go ahead and change this to 3S. Okay. And so now, before I start tackling this problem, let me think what I'm trying to find. If I want the gain or the ratio of V out over V in, let me find two things that describe that and are equivalent to that equation. Another way of saying this is, when I'm working in circuits, what do I know is proportional to this? I know that the voltage out, in this case, will be the voltage of my inductor, or it would also be the voltage of my resistor. And those two are both in parallel, so it's going to be the same thing. So now I have an idea a little bit of what I'm looking for. I can also call this whole section Z1. Okay? And on the bottom, I'm looking for Vn. So something in my mind that I'm thinking about is, okay, I don't have any current values. I don't have a signal for my voltage or an amount for my voltage, but I do have all of these impedances that I can work with. And so now that they're all in the S domain, I can really work with these impedances and find the ratio I'm looking for. So I'm going to call this Z1. You can also call it Zout if you want to. And then I'm also going to be looking for Zn. And Zn is the total impedance. So Z total, and then Vn is really the total voltage. And if you see here, our ratio, whether it's our impedances on this right side or if it's our voltages on the left side, they will be proportional to each other. So now I know where I'm going, and I'm able to find the ratio even though I don't have a current value or my voltage values, which is perfect and exactly what we want. So the first step that I'm going to do is, I see that R2 and L1, they're connected in parallel. I'm going to just draw it again over here. These two are connected in parallel. We said this was 2 ohms. So I'm going to go ahead and combine those two. You can use either equation for what you want to do. The equation I'm going to go for is, I'm going to call this ZL. I'm going to say 3S times 2 ohms over 3S plus 2. And this is going to be the value of my Z1. Okay? And this formula should look similar for combining two resistors in parallel or two components in parallel. It's that same idea. You can also do this equation above, 1 over R2, 1 over L1, all to the negative exponent of 1. These will both give you the same answers. Okay? So now my next step is, if I was to redraw my circuit one more time, I now have two components. I'm going to draw this as a box, and that's my Z1 value. And then I still have my resistor, my signal, and the rest of my circuit. I said this was 10 ohms. And remember, I'm thinking this is Vout and this is Vn. Okay, so now I'm getting pretty close to solving my problem. I have my Vout value. And so when I'm going to plug in what I'm thinking for Vout, it's just going to be my Z1 and my fraction. And now I need to find that Vn. And remember, I'm saying that the ratio is going to be proportional to those impedances. So now let me find the total impedance. The total impedance in this case is going to be R1 plus Z1 because now they are in series. It is one continuous current path. Okay? You can add those two in your calculator, and the value you should get for that number is going to come out to 12 minus 1.3 S plus 0.667. Okay, so this is my Z total right here. I'm going to go ahead and circle it. Okay. So now I found everything I need to find, and I'm going to rewrite that ratio one more time. Vout is equal, or over Vn, is equal to Z1 or Zout over Zn. I'm going to also do that operation in my calculator, and then I'm going to have it factor it out for me so I can get an answer that looks the best. My final answer for this problem is going to be 0.1667 times S over S plus 0.667. Okay, and I can circle this, and that is my voltage gain in this case. Thank you for watching the video.